Good morning, good afternoon, good evening. Welcome and thank you so much for visiting the channel. In this video, we will be discussing about regression and we will be learning about regression as a statistical technique, its types, examples, and evaluation models. Regression is a statistical technique for modeling a relationship between a dependent variable, or the outcome, and one or more independent variables, allowing for prediction, explanation, and also for hypothesis testing. The goal for regression is to predict and also explain how the changes in the independent variables influence the dependent variable. We have different types of regression. We have simple linear regression, multiple linear regression, logistic regression, polynomial regression, ridge-lasso elastic net regression, and also nonlinear regression. But we will be talking first about linear regression, multiple linear regression, and also logistic regression. Now, simple linear regression, this one, models the relationship between one dependent variable and one independent variable. For example, you want to predict the students' scores using the number of hours that they studied. Multiple linear regression extends simple linear regression to include multiple variables. For example, you want to know the impact of study hours, the teaching style, and attendance of the learners on their test score. Logistic regression. This is a special case of regression analysis. We have three classifications: ordinal, binary, and multinomial. When we say binary, it predicts the relationship between independent and binary dependent variables. The examples of the output of this regression type may be success or failure, 0 or 1, true or false, yes or no. Another would be the multinomial. A categorical dependent variable has two or more discrete outcomes in this regression type. For example, predicting whether a student will join a college, vocational or trade school, or corporate industry. Another is the ordinal logistic regression. Here, it applies when the dependent variable is in an ordered state. For example, formal shirt size. The outcomes would be extra small, small, medium, large, extra large. Another example would be the relationship between the number of hours students studied, teaching style, and attendance in passing or failing of the students. Regression is important in the field of medicine, education, agriculture, finance, and other industries. First application would be prediction. We could predict the future values based on historical data, for example, financial performance or predicting students' grades. Another would be the relationship understanding, like the example a while ago. Next would be risk assessment, usually used in finance and healthcare to evaluate risk factor. For example, predicting that the policyholder will claim insurance next year based on age, driving experience, or someone will default a loan. Another would be optimization, using regression in industries to optimize processes by understanding relationships among variables. For example, school wants to predict how well students will perform in final exams based on their study habits, attendance, and participation in extracurricular activities. Simple linear regression, as discussed a while ago, it is with one independent variable x and one dependent variable y. The equation for this is y is equal to beta sub o plus beta sub 1 x plus epsilon. So the assumptions for linear regression is that first we have linearity. There should be linear relationship between independent variables and the dependent variable. Independence, meaning residual or errors of the model must be independent of each other. Homoscedasticity, the variance of residual should be constant across all levels of independent variables. Normality, the residuals or the errors should be normally distributed, and no multicollinearity or not highly correlated with each other, the independent variables. For example, the relationship between the number of hours the students studied and the exam scores. Here's the data for 6 students. So we have our equation and we have to run statistical software here. Suppose we have beta sub O is equal to 50 and beta sub 1 is equal to 5. So our equation would be y is equal to 50 plus 5x. Suppose we want to predict the exam score of students who studied for 6 hours. That would be y is equal to 50 plus 5 times 6, the number of hours, that is equal to 80. Therefore, the predicted test score for students who studies for 6 hours is 80. Now, multiple linear regression, as discussed a while ago, it involves more than 2 independent variables, and this is the equation that we have. Assumptions of multiple linear regression is just the same with the simple linear regression, and also the dependent variable is measured on a continuous scale and there are no outliers in the data. An example: a school wants to predict the exam scores of students based on the number of hours they study, their attendance percentage, and the amount of time they spend on extracurricular activities such as sports or clubs. The school has collected data from the past semester for 6 students. This is the data. We have here the hours of study, attendance, extracurricular activities, and exam scores. These 3 are our independent and exam score is the dependent variable. Now, the first step that we have to do is to write the multiple linear regression model equation, which is the y is equal to beta sub O plus beta sub 1 x sub 1 plus beta sub 2 x sub 2. Now, this next step would be to use statistical software to fit the model. We could use Python or data tab, SPSS. Now, we'll have to interpret our output. This is the result. We'll have here r squared, adjusted r squared, the coefficient, standard error, and so on. The regression coefficient and interpretation. From the output, we have the following regression equation. Y is equal to 50 plus 3x sub 1 plus 0.5x sub 2 plus 0.2x sub 3. Beta sub O is equal to 50. If a student has 0 study hours, perfect attendance, and 0 time spent on extracurricular activities, the predicted exam score is 50. The beta sub 1 are hours of study, which is equal to 3. So for each additional hour of study, the exam score is expected to increase by 3 points. Beta sub O is equal to 0.5, meaning for each 1% increase in attendance, the exam score is expected to increase by 0.5 points. And for our beta sub 3, it is equal to 0.2, meaning for each additional hour spent on extracurricular activities per week, the exam score is expected to increase by 0.2 points. However, the coefficient is not statistically significant because its p-value is 0.16. This means that extracurricular activities might not be as strongly related to exam performance as the other 2 factors. Now, we'll have to predict exam scores. For example, a student score who studies for 6 hours, has 90% attendance, and spends 4 hours per week on extracurricular activities. Now, using our regression model, we'll have 6 hours and 90 and 4. The result would be 113.8, meaning the predicted exam score student would be 113.8. And the r squared is equal to 0.95, which means that 95% of the variability in the exam scores is explained by the model. Our adjusted r squared is 0.92, indicates a good model. Our p-values for hours of study and attendance are 0.018 and 0.040, while our extracurricular activity is not statistically significant because its p-value is equal to 0.16. Now, we can conclude that the multiple linear regression model shows that both hours of study and attendance are significantly related to the students' exam scores, and It means increasing study time and attendance are positively associated with higher exam scores. While extracurricular activities, in this case, does not show a statistically significant relationship with exam scores based on model's p-value. Logistic regression is used for binary classification task with two outcomes like yes or no. This is the equation. Assumptions of logistic regression. The response of variable is binary. The observations are independent. There is no multicollinearity among explanatory variables. There are no extreme outliers. Linear relationship between explanatory variables and the logic of the response variable, and sample size is sufficiently large. This is an example, the passing and failing of exams. And then we'll have to go over with the polynomial regression. It is a form of regression analysis in which the relationship between the independent variable x and the dependent variable y is modeled as an nth degree polynomial. So this is the equation, ridge and lasso elastic net regression. When we say ridge, it is a method of estimating the coefficients of multiple regression models in scenarios where the independent variables are highly correlated. Lasso, on the other hand, is an analysis method that performs both variable selection and regularization in order to enhance the prediction accuracy and interpretability of the resulting statistical model. Nonlinear regression, a technique that helps describe nonlinear relationship in experimental data. Evaluating performance of a regression model requires a different approach and different metrics that are used to evaluate classification models. We have r squared, and this is the formula. It represents the proportion of the variance in the dependent variable that is explained by the independent variables in the model. Adjusted r squared, it adjusts r squared for the number of predictors in the model, making it a better metric when comparing models with different numbers of predictors. Adjusted r squared can decrease if irrelevant predictors are added to the model, which helps in selecting the most relevant predictors. Mean absolute error, it measures the average magnitude of errors in a set of predictions without considering their direction. This is the formula. It gives an idea of how far the predictions are from the actual values on average. A lower MAE indicates a better fit. Mean squared error. It's similar to MAE but gives more weight to larger errors due to squaring of residuals. Now, MSE penalizes larger errors more than MAE. A lower MSE indicates a better model fit. However, since it squares the errors, it can be more sensitive to outliers. RMSE, or the root mean squared error. It is the square root of MSE and provides a measure of the average error in the same units as the dependent variable. Commonly used when you want to understand how large the typical prediction error is in the context of the original data. Now we have F statistic. It tests the overall significance of the regression model. A larger F statistic suggests that the model explains a significant proportion of the variance in the dependent variable. P-value for coefficients. P-values indicates whether individual coefficients in the model are statistically significant. Low p-value, usually less than 0.05, means the predictor is likely significant. We have residual plots. And this is the next one would be the the variance inflation factor, VIF, measures how much the variance of an estimated regression coefficient increases when your predictors are correlated. This is the formula, and a VIF value greater than 10 often give indicates high multicollinearity between predictors, which can distort the regression coefficients and make them unstable. So that would be all for regression. Thank you so much for listening.